Okay, let's start.
Thank you.
Henri.
Yeah.
The title is Determinoids, Determinoids and their multiplicativity.
Okay, so thank you for the introduction and 講演の機会をいただきありがとうございます。So I'm Henri from Shibaru Institute of Technology, master first year student. So here's the outline of my talk. So first of all, I'm gonna give an introduction on my research background. Then I will talk about the assembly of determinoid, and then talk about the basics of determinoids and some of the properties. And then I will talk about introduce my research theme and in details and give the results here. Okay, so first of all, the introduction. So during linear algebra class, we learned various facts about square matrices and, most importantly, use the determinant of the given matrix to solve different kinds of problems. However, in real-life situation, most of the problems involving matrices cannot be expressed by square matrices. Although there are some methods to reduce the problem by turning those non-square matrices back into square matrices, is there a more direct way to turn those non-square matrices? Is there a more direct way to study these kind of non-square matrices? In this talk, I will explain the determinant-like functional for non-square matrices called determinoid, and study its left multiplicativity. So whenever we talk about determinant of a matrix, for example A, the first thing we will think about is like this. The first thing we come up is if the determinant is non-zero, then A is regular. So if A is regular, then we know that determinant is non-zero. So similarly, for n by k matrix X, if the determinoid of X is non-zero, then the left inverse of X exists. So let's look at a quick example. So let X be a 3 by 2 matrix, this one, and the determinoid of X is -1. So I will explain it later on how to compute this. And the following three matrices are left inverses of X. So the inverse of a non-square matrices is not unique. So the first one is called normalized left cofactor matrix. So in this talk, I will explain how to compute this too. And the second one is called pseudo-inverse, which is the common way to find the inverse of a non-square matrix nowadays. And the third one is called by math instinct. Like you look at the matrix, you find it out by computing in your mind. So these three matrices means like this, times X on the left side, and you get the identity matrix of order 2. Okay, next, we're going to talk about the assembly of determinoid. So first of all, let K be a field, and Nk be integers, which satisfying this descending order. N is greater than K is greater than 1 or equals to 1. And we're going to define alternating K linear functional, D and K, on the set n by K matrix on over K, and we are seeing it as vector space Kn, direct product K times, and it satisfies this condition. So dnk of ei1 to eik is defined as -1 to the power of summing L over 1 to K, IL minus L, and the I is satisfying this condition. And the set E1 to En is the standard basis of the vector space Kn. And then the value dnk of x1 to xk is called the determinoid of x. X is defined like this, and denoted as that n by k of x. Okay. So let's have a look at the example. When n is 3 and k is 1. So first thing, this is a column vector, and we want to compute its determinoid. And we rewrite it as the free linear functional form. And by linearity, we have this line. And by definition of D31, it should be -1 to the power of I minus 1. So it's like this. Simplify it, we get this, x11 minus x21 plus x31. So in general, we have that n by 1 of x is equals to the summation of alternating sign of all entries. Okay, next is a bit complicated when k is 2. So first of all, we write it in free linear functional form again, and then expand it by linearity. And remind that d32 is an alternating function, so the terms having the same entries will disappear or turns to 0. And grouping it together, simplify it by definition. So d32, the definition should be I minus 1 plus j minus 2, so it's like this. Simplify and rewrite it, we have the definition of a 3×2 determinoid, like this. So the definition is quite complicated, so I'll introduce how to compute the determinoids, like how we compute determinants. So the first method is called the Radic's definition. This method is calculating the determinoids by summing over n choose k by k determinants, like this. So we take k rows out of n rows and arrange them in ascending order. And this one is the one we just discussed. And let's have a look at the example. So 3×2 matrix again. And we are choosing 3×2, 2×2 determinants, so 3×2 is just 3. So possible combinations are 1, 2, 1, 3, and 2, 3. Substituting it back here, we get this line. Simplify it, get this, and determinants, like we already know how to compute it, so like simplify it and rearrange it, we have this one. And this is the same as the previous slide. Okay, the second method. The second method is called the general expansion formula. So if some of you can remember, the definition of determinant has some similar one, and it's called the Leibniz formula. And this one actually is the generalized version of Leibniz formula, except for the subscription here, it's not the symmetric group of all n elements, and this is not the usual signum function. So let me explain what it is. So first of all, SIK is the set of injections from the index set k to the index set I. K is less than n. And the signum nk of sigma is defined like this. So here we have the same term again. And the signum function here is the usual signum function. And the set I1 to Ik is the image of sigma arranged in ascending order. So let's have a look at an example again. 3×2 matrix again. So we have to consider the set of all injections, 1, 2, 3, 2. So like 1, 2 to 1, 2, 3. So there are 6 elements. So previously we talked about 1, 2, 1, 3, and 2, 3. And here we consider about the reverse version of it. So 2, 1, 3, 1, and 3, 2. So there are totally 6. And we compute the signs. So due to the complexity of calculating it, I just list out the results here. And substituting back these 6 results to the general expansion formula, we get the determinoid. So this one is the same again. Okay, the third method, the last one, expanding along the jth column. So like it's just the usual way to compute the determinant. But like here, k is greater than or equals to 2, because like if it's 1, then just like I said before, it's just summing over all entries with alternating signs. And so this one is just like the cofactor expansion in determinants. And here xij is the notation of a n-1 by k-1 matrix yielded by removing the ith row and jth column from X. And here I'm going to give a corollary of normalized left cofactor matrix, as this is the usual way of how we compute inverse of square matrix. So if the determinoid of X is non-zero, then a left inverse of X exists. And the k by n matrix whose ij entries is given by this formula is one of the left inverses of X, called the normalized left cofactor matrix of X. So let's have a look on example on how to expand it along J column. Like for simplicity, I expand the first column. So take the first entry out and cross out the first row, first column. We have this cofactor here, and the sign is listed here. So do the same thing for the rest of 2. Simplify it, we'll get this. And the way of calculating 2 by 1 determinoids are the top subtract bottom. So x22 minus x32 here, and do the same. Rewriting it, we'll get the same result again. And about the normalized left cofactor matrix, I use the general way. So like the determinoid of x is non-zero, we can do the division here, and then the 2 by 1 determinoids again. So I already computed the sign. So like this one is exactly the same as the determinant. And compute it, like listing all out, we'll get this one. So okay, and now I would like to talk about the properties of determinoids. So by previous slides, like we already know that it has multilinearity and alternativity in columns, just like the properties of determinant. Except it has one more property, which is like this. It's weird, but because like this one is originally proposed as a proposition, but due to its interesting result, it become a property. So what here is, so let 1 tilde be an n by 1 matrix, so like a column, with all entries are 1, so a column of 1s. Then the determinoid of the augment matrix x and 1 tilde is equals to the determinant of x if the difference of the rows and columns is odd. If it is even, then it's equals to 0. So what this means is if we are dealing with n by n minus 1 determinoids, we can just add a column of 1s here, and we can switch it back into normal determinants of order n. Okay, next I would like to talk about the multiplicativity of determinoids. So like in normal determinants, we have this multiplicativity property, but like for determinoids, unfortunately, it only has the right multiplicativity. So for any n by k matrix x and k by k matrix y, the determinoid of the product xy equals to the determinoid of x times the determinant of y. This is true, but like if we reverse it, it's not true. So let's have a look at a concrete example. So consider the following 3 matrices: a 3 by 2 matrix A, 2 by 2 matrix B, and a 3 by 3 matrix C. And their determinoids are 3, 5, minus 1 respectively. Okay, now let's consider the products A, B, and CA. So both of them are 3 by 2 matrices, and the determinoids are 15 and 0 respectively. So like usual determinants, determinoid of AB can factor into determinoid A times determinant of B. So 3 times 5 is indeed 15. However, for CA, it's not true. So determinant of C times determinoid of A, minus 1 times 3 is minus 3. It's not 0. So this, in here, we can raise a question. What kind of matrices satisfy the left multiplicativity of determinoids? So I will introduce my research theme here. So let's we will introduce the following sets, these 2 sets. For 1 less than or equals to k less than n, the first set is called GPNK tilde, where we take the elements of general linear group, and such that for any n by k matrix x, the determinoid of x equals to 0 if and only if the determinoid of the product ax equals to 0. And the second set is GPNK. We have similar settings here, except for the latter part. We change it into the if the determinoid of the product ax equals to the product of determinant A times determinoid of x. So our research theme is the description of these 2 sets, and GPNK tilde describes the symmetry of 0 locus of the determinoids. And GPNK consists of square matrices satisfying the left multiplicativity of determinoids. And we have the the following inclusions. GLNK includes GPNK tutor, includes GPNK. And in fact, GPNK tutor and GPNK are subgroups of GLNK. So in fact, it is a group. And here are the results at this stage. So first of all, when k equals to n minus 1, we can rewrite GPN n minus 1 like this. So what this means is for any element in GPN n minus 1, every row of the row sum is equals to 1. And GPN n minus 1 is isomorphic to the affine transformation group. Okay, and second, for k equals to 1, we have we can rewrite GPN n1 tutor like this. So what this means is for any element in GPN1 tutor, there exists a lambda, a non-zero scalar lambda in K, such that the determinoid of each column equals to the alternating sign of lambda for any I. And similarly for GPN1, like I told you before, like it's a inclusion relation. So it's similar, except for GPN1 it's like it restricted into the determinant only, not a lambda, but like a determinant of itself. And lastly, I would like to introduce identities, because we like them. And first of all, the original identity is called the Determinant-Jacobi identity. So for n by n square matrix, when we're removing a row and a column, we will write it as ij, the subscription. And if we remove more than one, we'll like use a set notation here. So what here is the determinant of x times the determinant removing first row and last row, first column and last column, the product of these two, equals to the determinant of removing last row, last column times the determinant of removing first row, first column. Subtract the determinant of removing first row, last column times the determinant of removing last row, first column. So maybe it's hard to understand, like hard to see what it is. So like let me draw it out. Here. So this one is the original one. This is the middle part of the matrix. This one is the left upper corner, right lower corner, right upper corner, left lower corner. So this is just like a 2 by 2 matrix determinant. A, D, B, C, like that. And for determinoids, we have also something like we have the middle part, but like for the n by 2 case, we are missing this part. So here's my proposition of the Determinant-Jacobi identity of n by 2 case, like this. Instead of a product of two determinoids, there's a difference of two determinoids, and the right hand side is still the same. So maybe you ask why it's not 1, because 1 is already simple enough, so we don't need that identity. And next, the n by n minus 1 case. So like recall this property, and substituting it into the Determinant-Jacobi identity, we have this identity here, like a hybrid form of determinoids and determinant here. So this means we are not doing anything. We are not taking any rows, columns out of it. And lastly, I propose an alternate computation method for n by 2 determinoids. Like if we can compute n by 2 determinoids as two n by 1 determinoids of the product of them, will be easier. So the result is as like this. It looks might be complicated, but if like I'm still thinking of a slogan on how to compute this term, and in fact this might be easier for human beings, but like definitely not for machines, because like this is already increased quite a lot of computation costs. So I will put some more effort on this term to make a slogan out of it. And here are the references. So this is the end of my talk. Thank you very much. Hi. N by 2. はい。
N by 2の2を上げていっても、ある程度似たようなものが成り立つと期待しているっていう感じなんです。
つまりn×3から予想はそうですけど、でもどうやって証明するはまだ考えています。
形はその3、4にしたときにもう本当にとても複雑になるわけではない。
わけではないです。ほぼ同じと思います。予想は。予想はまあほぼじゃなくて、まあ、全く同じと思います。前試したはこっち n×n-1 の場合でこんな計算方法じゃなくて直接さっきのですね、ヤコビコード式を使って、まあ、答えは合ってますけど、でもたまに合ってるかどうかまだわからないですから証明はまだ考えています。Like how to approach the proof is still in process. はい。
じゃあこの続きはじゃあ n×3 とか機能されるということですか。
コード式の話ですか。
はい。
まあそうしたら